I'll give you an overview. But one thing I want to ask you to do is to ask questions. Does it pay off to ask questions? Does it pay off to ask questions? Yeah. Because if you ask a question, you'll get another one. Okay? That's why I want to keep it as interactive as possible. Okay, let's take a look. Okay, so we have a wrong schedule. Doesn't mean that we need to go to the end. What is important is that, you know, we all have the interactions. We already have the possibility to chat. And I'm more than happy to use the board to stop, to slow down. But let's say the general overview is kind of ambitious. So we'll start with some representation of the spaces. Introduce very standard things. So I know that it has been done by Jesus yesterday. What I think is important is to have different views presented by different people, because then it's much easier to understand once you have different angles on the topic. We'll go to Euler characteristics, something simple yet surprisingly powerful. We'll discuss the use of it in the data science. Then we'll move to statistics, hypothesis testing, and discuss the family of visualization methods. Then there will be time for fun, games, and music. So the stuff you heard, Sebastian Reich, the violin phase. You may get some answers over there, or may not, we'll see. Right here. I'll mention the use of TDA in various aspects, but including also pure mathematics. Then we'll shift gears to discrete Morse theory. I want to speak about Whitehead's torsion as we did on the way here, but maybe we'll get there. And maybe we have time, we'll speak a little bit about the dynamical system. Yes. Yes, we are. Okay. So, since you asked the question, there's an answer to you. And I'll keep it up for a moment. No, but I'll share it later on. So no worries if you want to take. So that's a link to a Google Drive with all the materials. So I didn't put up the slides yet, but I will put up the slides. But all the Jupyter notebooks. So you can even try to use it on your phones if you use Google Colab. So if you don't have a computer, there's a trick. I'll tell you how to use it on Google Colab, even on your phone if you want. So I'll be doing some examples over there. Just tell me whenever you're ready. I mean, you can use your phone. Oops, sorry. By the way, so those are traditional Polish sweets from Warsaw. I got some more, so can ask more questions. Okay, whenever you're ready, we can actually go to introductory phase, and then we'll try to talk about ideas, some of the mathematical and computer science meat of the thing. So I always start with the quote of attributed to Gunnar Carson about the shape of the data. And I always say that this is not something surprising. So it were not the topologists who actually came up with this. So it goes really way back to statisticians. Over here we have an example, very standard example of a linear regression. Very, very standard tool in the statistics. So if you have a data that happens to be like this, you can try to fit a line. So you are having a line, it's parameterized with a polynomial equation, first degree polynomial y equals ax plus b. And you can try to find the best value of the parameters a and b using, for instance, least square minimization. And then you fit the line. And the line is useful because it is a model of your data. At the end of the day, you don't care how many points you have over here. You may have really a lot. But once you have the A and B parameters, you have a pretty good idea what's the value of Y given X. So it gives you a model of your data set. However, the underlying reason why it's actually useful and why it works is that your data happen to have a linear shape. So this is where the shape came into existence, became important. But not all of the, actually, world is not linear. Most of the phenomena are somewhat non-linear. So, so if you look at, for instance, at some sort of periodic data sets, look at some cyclic behavior. If you are working on the chaotic thing, you may get something like a figure 8 in butterfly attractor. If we have time, we'll be speaking about all of those. When doing topological visualization, oftentimes you realize that the data sets happen to have a shape of, a central thing, which is kind of a normal state, plus what we call it flares. So region of points going away, which are kind of abnormal state. So it may be that the central thing is a healthy state, and you have different types of diseases coming from some patients' data. So all those data sets, they have different shapes. And if we take an inspiration from this very algebraic way of fitting a polynomial into the system of equations, you can try to do it. Of course, you will overfit by far because a priori you do not know what is the shape of your data. And keep in mind that our mindset should be that our data are somewhat high dimensional. So it's very hard for us to understand what's the real shape. What we are trying to do is to get some sort of features that will tell us something and allow us to make an inference about the data set. So that's one piece of introduction. And as I mentioned, of course, the statisticians are doing the same, are asking very similar questions for many, many years, or even not centuries. So if we really want to kick on the topological data analysis, let's go back to the statistics. And actually, they already provided a motivation for us why the shape of the data is needed. So that's my favorite classical example. I actually forgot to put the reference. So this is by Anscombes, 1973. So back in 1973, we provided a data set consisting of 4 different samples. And that's actually a cultural difference. So if you are doing machine learning TDA, we typically say a point cloud. And when you are doing a statistics, you are saying sample. And that's the same thing, a collection of points. So because we're speaking about statistics, we have 4 different samples. Clearly, you can see that they do have a different shape. However, if you compute some summary statistics on those, then you will realize that, for instance, if you compute the average value of the x coordinate, maybe the average value of the y coordinate, or the standard deviation of x or standard deviation of y coordinate, or if you take this linear regression and then fit the line, you realize that all those summary statistics will give you almost exactly the same numbers, regardless which data sets. So they have all the same average value of x, average value of y, standard deviation of x, standard deviation of y, and they are all fitted by the same line if you are doing least square minimalization. So if you just do blindly the statistics without actually scatter plotting the data sets, you will think that they are very similar. Yet, our visual cortex in our brain tell us that they are different. So this is one of the motivation. A much more extended example of exactly the same phenomena has been provided, and I do provide a reference by Alberto Cairo over here. It's like 2016-ish. The same property. You see, they do have very different shape, yet the summary statistics up to the 3rd or 4th digits of precision, it's called Datasaurus, right? Because of that guy over here. So they do have the same value of the statistics, very different shapes. So what are the messages we can take out of this? There are a couple of them. So first of all, what statistics is doing? Statistics is about statistics. The statistic is typically a number, like an average, standard deviation, maybe a higher moment. So it is about computing a collection of numbers to characterize the properties of samples. But as we see, sometimes those statistics are not sufficient. And if you look at the original paper of Anscombes, or maybe 2016 Datasaurus paper, the message is always visual, but you should always visualize your data. So before you start blindly applying machine learning or artificial intelligence methods, try to look at your data using whatever tools you have and make sense out of it. To understand if you are using your tools properly, what you are doing may actually sense. And that's a very good advice. However, if you are doing real data analysis, you immediately realize that most of your data sets are not two-dimensional. So you cannot simply scatter plot them. And this is precisely where the tools of topological data analysis are coming into rescue. Okay. Do I have anything? Yes, that. So essentially, the general pipeline is we'll be starting from a point cloud or a sample, if you wish. We'll do some feature, topological feature. I'll discuss a number of them. And then based on this feature, by looking at this feature, by plugging it in, for instance, the standard statistics, machine learning, we'll try to get some inference based on it. So that's the general idea. And let me discuss the first part. So the first part, well, we start from a collection of points, and we want to compute some feature. The most standard one, again, was briefly introduced. I will also mention it over here, is based on the concept of homology theory. And in order to have a homology theory, we need to move from a discrete collection of points, which by itself are just a discrete metric spaces, into some combinatorial representation, which the most typical one is a sort of simplicial complex. So simplicial complexes are a collection of simple objects. So over here, we don't have a simplicial meshes, but typically we are speaking about vertices, edges, faces, and volumes. In general, cell complex, they have dimension 0, 1, 2, 3, and higher. And there's some condition about those simple elements fitting nicely together. And once they fit nicely together, you can have a finite representation of an infinite set that you can use to compute some characteristics. I'll get more into details with it, so just bear with me. So the basic definition, the basic concept, which is also the most obvious implementation if you are actually working with a computer code, is this idea of an abstract simplicial complex. So if you look at the first line up here, this is just a collection of sets, such that if I take any set from this collection and the subset of this subset needs to be an element of the collection. So let's take a look at an example of this tetrahedra. So that's an abstract simplicial complex representing the tetrahedra. And if I take any element of this collection, say, for instance, the BCD, which is a triangle, this is BCD, this is this triangle in the back over here. Any subset of this collection, say this one, BD, need to be an element of this collection, and indeed it is. And that this property of a collection of sets being closed under the operation of taking subset is the condition that we require from an abstract simplicial complex. Now, that's if you actually assign coordinates to your vertices, you can think, if you assign them in the right way, you can have a geometric representation. So then you really have an object with some geometry, and some interesting questions of what's the minimal embedding dimension of a simplicial complex. You can look at the Whitehead's theorem. We are not going this way, but this will be the building blocks of our stuff. And again, it appears in topology, but it's also extremely widely used in mathematical modeling. So all the finite element based modeling is kind of based on the idea of decomposing your space on something small and simple and nice that fits together nicely. So this is probably the majority of use of the abstract, of the geometrical simplicial complexes. Okay. So let's start with the data. And our task is not to try to fit a model of the data, not to try to fit an algebraic equation, but get some sort of feature that you may think of as statistics on steroids. So it's like an average of a collection of numbers, but with much richer structure, with much more information. And it has some nice property, stable. Sometimes when I'm speaking to AI people, there are no black boxes. We can explain everything. And we do not enforce any model. So we are not trying to fit any particular type, degree of polynomial. It's mostly that we are trying to understand the data as they are. Okay. What do you see? Who said the circle? Okay, any other ideas? What? A cat. Okay, I will count it. Homotopy-wise, it's a circle. Oops. Okay, that's a wrong answer, but I will give you a one. Anybody see 19 points? Okay. I think you need some glasses, you know? Maybe two clusters. Which one you want? This one or that one? Okay. 19 points. Okay. So now normally I would say two answers are possible, either a cycle or indeed 19 points if I counted correctly. It's not homotopy type of a cycle because it's a discrete metric space. But we want, yes, that's the yes. That's exactly what we want to do. So persistent homology is kind of a tool to try to justify that what we are looking for is indeed something that may be sampled from a probability distribution, the support of which is centered close to something which is circular, or something that has a one connected component and one dimensional whole. And how do we do it? Well, the idea of moving from this discrete collection of points into something continuous is as follows. So we take a ball of a radius r, we center this ball in every of those points, and we take the union of those balls. This is what I said. So we take a ball, we take the union, voila. So I can actually homotopically retract this thing to a cycle. But then the obvious question is, how do you choose the radius, right? Of course, I choose it in the right way in order to make an illustration, but a priori, I do not know what is the right way. And therefore, what we are doing in persistent homology is we let radius r grow from 0 to infinity, and we'll be checking how the homology groups of this union of balls is evolving. And of course, what I'm going to tell you next is how to get from those union of balls, which is an infinite object, into a combinatorial representation which utilizes the concept of abstract simplicial complex. So this is what we are going to do next. But then in persistent homology, we'll notice that this union of balls have one connected component and one non-trivial cycle in dimension 1. And this cycle, there may be some more cycles. Maybe there is some small cycle formed over here. When I take a union of when I take the small radii, but this big cycle over here, that it has the property that it persists across the wide correction of radii. So maybe, from a radius which is a little bit smaller than this one to a radius which is a little bit smaller than that one. So that's wide range of radii for which we see the same cycle in homology. And but maybe the difference between this big cycle and potential smaller cycles that may appear on the way, which is for the width of the radii parameter for which it persists, and hence the name persistent homology. Okay, so now we need to take a step and take this union of balls and somehow make a combinatorial representation of this union of balls. And there are a few ways. I'll discuss it, and then we'll briefly take a look at some software implementation. So the most standard. So again, let's do it formally. So for every procedure, you need to define an input and the output. The output will be a simplicial complex. The input is a collection of points, and we have some metric. And there are two standard ways of assigning an abstract simplicial complex to a collection of points in a metric space. So the RIPS complex, it actually only works when it works for a general metric space. Czech complex, you really need to have an embedding to some sort of Euclidean space. But let me start from a RIPS complex. So we pick a level epsilon, that's the radius of the ball, and I have a collision which I should remove. So imagine that this n is a k. So we have a simplex supported in P0 to Pk, if and only if I take any 2 points from this sub-collection, the balls of the radius epsilon over 2 will have non-empty intersection. So in other words, the distance between Pi and Pj, when Pi and Pj are vertices of the simplex, is not greater than the epsilon. And if that's the case, then this collection of points constitute a simplex. And of course, you remember the condition that a simplicial complex needs to be closed under the operation of taking subsets. So if that's the case, that every pair of those points is not farther away than epsilon, then every subset of this point will also have the same, this collection of points will also have the same properties. And therefore, that thing is an abstract simplicial complex. So for a Czech construction, it is a little bit more demanding. So we say that this subset P0 again to Pk, sorry about the collision. If we take the union of balls of the radius epsilon over 2 and take the intersection of those two, all of those balls, and if this intersection happen to be non-empty, then we say that this collection over here constitutes a simplex in a Czech complex, right? Because we are looking at the intersection of balls, again, that should be embedded into something, so general metric space is not good enough. It's typically defined on the Euclidean space. Okay. So let's take a look. So I have a collection of 4 points, and I am going to increase my epsilon and then build a RIPS complex out of it. So if the epsilon is small enough, it's smaller than the distance between the closest point, we'll just have 4 vertices. So vertex by itself is a 0-dimensional simplex, but then we increase the epsilon, and we increase it up to a point where the two closest points get connected. Two closest points gets connected. So let's say that those are the diagonal one. Once they get connected, so this edge has a length epsilon, or the two balls happen to have non-empty intersection, then the pair of vertices constitute 1-dimensional simplex. And our simplicial complex has 4 vertices, 4 0-dimensional simplices, and 1 1-dimensional simplex. Then we increase the epsilon a bit further. And let's say that, those 2 points are equidistant from the third on the left. In which case, we are adding both edges. But that's not the only thing we are adding over here, because, well, for that level of epsilon, we will have all the edges that constitute this triangle or two click in our graph. The whole triple also constitute a simplex, because again it has the property that for every pair of edges, the distance between any pair of edges is less or equal than epsilon, and therefore we also put this one triangle or 1 2-dimensional simplex. I'd say that this is the next edge to appear. If we increase our epsilon level a little bit further, we get one additional edge. With addition of the last edge, we also add the triangle for the same reason as before. And there's one more edge that come to the play, which actually, and there's a lot of happening between this picture and that picture. So over here we have this diagonal edge, but thanks to it, we also have a 2-dimensional simplex over here. two-dimensional simplex over there, but also we have a three-dimensional simplex because right now, all the points, all the 4 points have the property that a distance of any subset of a size 2 is less or equal than epsilon, and therefore we have a 2 simplex. So that's a RIPS complex, and actually what we did is we went through a filtration. So it's not just a one fixed simplicial complex, but we have a sequence of nested subcomplexes, which is what we call the filtration, and it will be a very important object in persistent homology. Okay, so I defined for you in the wavy RIPS and Čech complex. Any questions about that? No questions? Any question? Question, no question? No question. Okay. You need to make sure that, different people are asking questions because I don't want, some guys over here to get diabetics because of it. Okay. So what's the difference between the RIPS and Čech? Do you really need those two constructions? And again, let me remind you, so in a RIPS complex, a simplex is added if all the edges are in place. But in the Čech complex, we need to have an empty intersection of all the balls. So that's the difference. This is the actually the simplest situation when we have a difference between RIPS and Čech complex. Namely, you see we have a hole over here. It means that if we take an intersection of all those 3 balls, it will be empty. So we won't have those 3 points will not constitute a 2-dimensional simplex or a triangle in a Čech complex, but it will in the RIPS complex because we have all the edges in place, because we have all the mutual intersection. So again, RIPS complex is a triangle with, of course, all the 3 edges in the boundary and 3 vertices in the boundary. However, the Čech complex is just a hollow triangle, so it's empty inside. And this is what actually makes a lot of difference. And so if you think from a perspective, and I think I have nerve theorem on the next slide.
Czech complex. If the
Czech complex is better. Yeah. Absolutely. Yes, absolutely. So question is, why do we even bother about the RIPS complex? And there are a few reasons. So first of all, again, in order to have this non-empty intersection or this hole, which we have over here, you really need to have an embedding into some Euclidean space, right? If this is a general metric space, discrete metric space, you won't be able to check it. And many data that we are looking at, especially in biology, if we take a gene expression of U and U and U, they are not naturally embeddable in Euclidean space. So that's one thing. Second thing, in practice, sorry, I'll switch off the WhatsApp in a second. In practice, when you are computing the intersection of the balls, you are using some pretty standard procedure from a computational geometry, a minimal and closing ball of a collection of points. That's very standard procedure in computational geometry. However, in some cases, it is unstable numerically, and it costs to actually make this computation. So once you have a simplicial complex consisting of millions of simplices, and for every of those simplexes, you need to check if all the balls have to non-empty intersection. There is a price you need to pay in computational time, in computational costs. So those are the reasons why people still use Vittori's RIPS. Sometimes it's simply unavoidable, and sometimes it's quicker. Okay. You won't get another one. But you can ask the question. Okay. In this case, you won't have a question. Yes? Okay, so you all... Yes, you can, in principle. I'm not sure if anybody have done this, but you will have a preservation of the homotopy type up to this dimension that you are actually of the intersection -1. So it does have some meaning. So yes, of course, you can cut off some computations, And again, in practice, when you're doing computations, and we'll see it in the code, this is both with Vittori's RIPS and with the Czech, is, and I'll come to this in the next slide, I think. So you're not building the whole structure, because if you put your radius too far, then it doesn't matter how much memory you have, you will kill your computer, because you'll have exponentially many of simplices. So most typically, once we are generating RIPS or Czech complex, we generate it up to certain dimension anyhow. So that's kind of implicitly done already. Does it answer your question? Will you be able to catch it? Yes, you want another one?
It may not share method or the particular way. It may not share the radio for your variable quality top or the data, but it may change the scale or changes of the radio. For example, if you choose another method for the not only the Euclidean, another key method, it makes it's done.
Oh, yes.
It's all the changes about the
Yes. So yes. So if you use different distance, okay. So let's try to decompose your question and let me make sure I understand. So if you are in Euclidean space, there's the equivalence between the metrics that are coming from a norm up to a scaling factor, you'll get the same thing. However, in very high dimensions, and I hope we'll also get to this one, the concept of metric doesn't make sense. And I'll explain why in a few slides. Typically doesn't make sense. So the question about different metrics, so if I, for instance, have a Euclidean metric and, for instance, a cosine similarity, which is not a metric, but a similarity measure, how the topology is related, that's a very good question. And I don't know the general answer to this question. But let's say at the moment, the Vittori's RIPS depends on this metric. So it's a function of the metric. If you take another metric, you'll get a different complex. If you take a metric which is comparable in terms of the sandwich inequality, so you have one metric. So the sandwich inequality, you have D1 and D2, which are metric. On some set X, and if we have a sandwich, and if I put a big quantifier over here, and if that's true for one of them and the other, and also a similar inequality is true if I exchange 1 and 2, then we, of course, for different constants, then in principle, you'll get some nice transformation of persistence diagrams. But if that's not the case and you don't have equivalent metrics, then in principle, you can get arbitrary differences.
if they are thinking, okay, or do you really get something that you can?
Okay, so I was speaking about transformation of persistence diagram, which I haven't defined yet. Information category, I mean, there are a few things that need to be defined in order to make your question precise. So I suggest we carry on and we take it over over the break, okay? Any more questions so far? What's which complex? Czech complex.
Here. Okay.
Uh-huh. Uh-huh. Yeah, because both are convex. Both are convex. So So you're asking if, okay, so let's go back and make sure I understand the question before I give an answer. So if there is an empty intersection between those three balls, it will be in the barycenter of the triangle, spanned by the vertices. And therefore, I think you are asking if they are in the convex hull of the points. And the answer is yes, because they're in the barycenter of this triangle, which is by definition the convex hull. Yeah. Yeah. I mean, for every triangle, the barycenter is on the interior or in the boundary if the triangle is generated. The triangle is degenerated, so you may have a triangle when, I have, let's say, 3 collinear points. That will also give me a 2 simplex, but somewhat degenerated. But again, the barycenter will be somewhere on this line. You cannot get it out of the convex hull. Okay. The computing what? I mean, okay, so we can discuss the mean ball. It's a procedure from computational geometry, which we use under the hood when constructing Czech complex. And yes, I mean, the ideas like this are used over there in this procedure. Absolutely. Can come later to get this one. All right. So let's see. Yeah, I want to speed up a little bit. So I'll skip the nerve theorem. So this is what I mentioned. This is what I mentioned. Somebody asked, you asked about the cutting the dimension. So the thing we should be careful about is if you put your radius too far, for instance, the radius being comparable to the diameter of your collection of points, then you expect to get, if capital N is the number of points, you expect to get n choose 1 vertices, n choose 2 edges, so every 2 points will be connected, n choose 3 triangles, etc., etc., etc. That thing sums up to n factorial, which is exponential with n. So if you understand exponential numbers, well, before you start running any persistence code on your computer, better to save your previous work. Otherwise, you may not be able, if the code will consume all your RAM. But also a way to deal with it is you typically try to restrict the maximal radius, but you are also trying to restrict the maximal dimension of the simplices. So for instance, except from very, very particular configuration of points and the Vittori-Rips complex, if you are, for instance, starting from a planar collection of points, it doesn't make sense to generate anything above, tetrahedra, or even triangles in this case, because we don't expect on the planar data set higher dimensional homology groups. Again, it's not entirely true. If you're doing Vittori-Rips complex, you can get homology in arbitrary high dimensions, but they are very short-living homologies. Okay? So there are some tricks. But there's also another way to fight with it. And again, it's to bring geometry back to the game. So and it's actually the basis of the idea of alpha complex. So we think about the problem over here. So we don't want the ball centered over here to meet with the ball centered over there. And the way to do it, and actually I should actually come back to the nerve theorem. So the nerve theorem, so over here we've been speaking about the union of balls centered in the collection of points. And that's one of the possible examples of a covering of a space. Covering of the balls centering some collection of points. But in general, there's this very, very strong result going back to 1920s called nerve theorem, which says that you have a collection of open sets such that the intersection of any subcollection is either empty or contractible, meaning I can continuously deform it to a point. And then the nerve of this correction which is a simplicial complex. So what's the nerve? I should actually speak a little bit about it. So the nerve is an abstract simplicial complex whose vertices are the elements of the connection, this collection U. And if I have a subcollection of those elements which have no empty intersection, then I put a simplex of appropriate dimension over there. And this way I'm getting a nerve complex. And the nerve theorem tells me that if all the intersections are either empty or contractible, then the homotopy type of the nerve complex is the same as the homotopy type of the union of those cover elements. And okay, so we need to think for a moment how to ensure that the intersections will be either empty or contractible. And the very nice sets which are contractible are convex sets. Because if a set is convex, and I'm kind of in the center of the set, then I can have a straight line going entirely in the set to any point over there. So I can do the contraction across those lines of the whole set to me. Therefore, it's contractible. And we know that intersection of two convex sets is convex, and therefore any intersection will also be convex and therefore contractible. That's why union of balls actually satisfies the nerve theorem. But once we are bringing back geometry to the game and introducing the Voronoi diagrams, they are also convex. So what is the Voronoi diagram? So for a collection of points, let's say in the plane, we are dividing a plane, we are making a tessellation of a plane into regions. And every region, say this blue region over here, has the property that every point in this region, the closest element of my initial collection of points, or my initial collection of vertices, is this vertex over here. So, you know, it's like you are in the city and you always want to go to the closest shop to buy coffee, right? So you are in the Voronoi cell of your closest, whatever you like, Starbucks or some other coffee place, right? So that's very much the same idea. It's not difficult to prove. So those regions correspond, so the region of the points which are closest to a given vertex, they are called Voronoi cells. It's not difficult to show that they are convex. So, okay, we have Voronoi cells that are convex. We have balls that are convex. We know that intersection of convex sets are convex. So if I start intersecting balls with Voronoi cells, I'll get something convex. So it satisfies the nerve theorem. Well, we can build a nerve. But look, right now we have a geometry back into the game, and it will never happen that, you know, a ball intersected with this Voronoi cell will intersect with the ball intersected with this Voronoi cell, because though they are distinct, they have empty intersection. So this way we are able to localize our simplicial complex, and yet we are still taking advantage of the nerve theorem, so we have the same homotopy type as the Čech complex. And actually, if you look at the papers in computational geometry, they're able to prove that the size of this alpha complex will be linear with respect to the number of points. The size of the Čech complex will in general is exponential of the number of points. So you get a lot of advantage. Of course, there are some computational costs because you need to generate the Voronoi diagram on the way. There are efficient tools to do it. So, and we'll also speak a little bit about that. And I also mentioned, so we had a discussion about metric.
What? What's the direction?
Okay, so here, the devil is hidden in detail. So let me have my coffee. Yes, it's linear in every dimension. However, what do I mean by linear? And here's the devil. So if n is the number of points, sorry about that, and the complexity is big O of n. What does it mean? Well, it means that there's a function. Essentially, it means that this is a function which is always bounded by something like c times n. That c constant depends exponentially on the dimension. And this is where it's hidden. So it's always linear, but when the dimension is growing, that thing is becoming ginormous. And this is why Voronoi cells in higher dimension are not practical. Okay? Any other questions?
That was it. If your data is embedded in the state of that, and it's also done with video tool at most of.
That's correct, yes. Yeah. Well, in generic case, so what do I mean by generic case? So in the planar, if I take 4 points, which are exactly on the square, then the Voronoi cells will be like this. And you may have a tetrahedra over here. So what I told you was true with probability 1, because those configurations are, of the probability 0. But it may happen, and you may also figure out the, higher dimensional intersection, but that's not generic. Okay? Help yourselves. Any other questions? Okay. Oh, so we are speaking about metric, and this is the key point of topology. So if you ask me philosophically why topology, not geometry, and the answer is because geometry is kind of rigid. Right? We have angles, we have things that we need to preserve. Topology is really about the proximity, right? So I'm looking at my nearest neighbors, and maybe I don't care, about, I do, but let's say you are not my direct neighbors. But the distance doesn't matter. It's only the abstract concept of the neighborhood. So we need this concept of distance. And if your dimension is going higher, and that's very typically what happens when you are working, for instance, with genetic data. And the concept of the dimension is becoming tricky. And here's why. So we have, you probably heard about the thing which is called curse of dimensionality. One of the aspects is a concentration of measure. So let's take a look. So here's the question. If I take a box, which is formally that thing, what's the volume of that box? Can anybody please tell me? 1. It's true. Okay, let me take a bit smaller box. So imagine that I cut off, from every side the stripe of the diameter epsilon. Right, so all of those have diameter epsilon. So the volume of this thing V, don't jump ahead. Yes, it does. It's 1 minus 2 epsilon to the power n, right? Because, the length of that thing is 1 minus epsilon minus 2 epsilon. I mean, that thing, for epsilon positive, this thing over here is strictly less than 1. And as you notice, if n is high enough, the volume of this thing is going to 0. It means that the whole measure of a box is concentrated very close to the boundary. It's very, very unintuitive. But that's this is what happens when you have uniformly sampled data from a unit box. It's not typically what we expect. So the reason why we can actually do something is because we believe in a manifold hypothesis. So typically we believe that the data are not just uniformly distributed in very high dimensional space, but there are some laws that actually constrain the data. Make sure that the x coordinate and the y coordinate from the Euclidean coordinates are somewhat related, and therefore we call it a manifold hypothesis. So another, do I have it better now? Another not obvious thing in very high dimensions is if we take a collection of points uniformly distributed, and we expect that the distance between any 2 points will be more or less the same, regardless of the points. And I mean, here's a short explanation. So we sample uniformly. The expected value of the difference between the two chosen coordinates is 1/3. So if we compute a Manhattan distance, it will be 1/3 to the power n, regardless of the points. And that's also, well, so what does it mean from the perspective of what we've been discussing? So essentially it means that distance doesn't have a meaning, because when you are growing your balls, they are in separated clusters until they reach this 1/3 to the power n value, and then everything gets connected at the same time, like this. Well, you won't get much information out of it. And that's something to be aware of. That's a big problem. So I won't give you a solution, but generally remember, metric sucks in high dimension, so you need to be careful. There are various ways to try to navigate around it. So what we typically do when analyzing biological data is to try to select important variables, to remove something which is not important. You can try to do dimension reduction. You can try to use other measures, not the distance, but some sort of similarity measure. I mentioned cosine similarity. Maybe we'll have time to go into some of the examples. And, well, they behave a little bit better. But ultimately, when you are dealing with high dimensions, this is what you are going to face. And you will need to face this challenge and do your best to actually get over it. Okay, so I'll try to, yes. Okay. Maybe let's do it offline. So you just compute an expected value of a difference between I and j coordinate, and then this is essentially you need to compute an integral. Okay. So here it is. I'll give you a recipe, but I won't write it down right now. So if you take 2 points, so imagine that we are sampling x and y from the uniform distribution on an interval 0, 1. What I want to compute is the expected value of a distance between x and y. And what I'm claiming is that this is 1/3. Okay, so I won't do the computations right now. I'll need another shot of coffee. And this is my claim. And if this claim is true, and if you are computing, for instance, Manhattan distance on the high dimension, you are just summing up those two numbers. Right, so it wasn't. So this is in dimension 1. But if we look at the Manhattan distance, in dimensions, then the expected value of those guys will be n/3. Regardless of the points. And that's what I meant in. Sure.
Very likely, but you will discuss it.
Yeah, but not a lot of points, but points in very high dimensions. Yes. You come back and try this one. They're also good. All right.
That's our problem that you mentioned. In best of basic technologies in past several programs, and that's very method that where it might often deal with more for supposed that data.
Yeah. Well, we'll have some comparisons. Right. So they should be used together. You remember, TDA is not a silver bullet, not very close. It just provides an additional collection of tools. But you should use PCA. You should use nonlinear dimension reductions also in order to try this point on your data. Okay. Okay. Let's see. Oh my goodness. So it's meant to give you an idea of homology. And of course, I'm not going to define it. That would require a few lectures of the standard algebraic course, algebraic topology course. But the whole idea of topology, excuse me for a second. So the whole idea of topology is about connectivity, and you should think about this as generalization of connectivity in graphs. So in graphs, we are looking at connected components, and those are the connected. This is what homology in dimension 0 is measuring for us. But homology allows you to lift this idea to higher dimensions. So for instance, in dimension 1, we have this hole over here, and we'll see it as a generator in one-dimensional homology, a hole that I can actually cage that thing. If we take a ball, so for instance, my coffee mug, I'm claiming that there's a generator in dimension 2. As an evidence, I can just, rotate it. And because my coffee is not dropping, it means that there's something that prevents it from flowing off. It's very much like in the ball or something. So it shields the inside from the outside. This is the dimension 2 generator. And we'll have, on the next hour, around the lunchtime, I think, we'll play a little bit with this software, which is called Goody. So we'll be doing some of the computations over there. And let's see, so I have 1 minute left, but I think it's a good moment to stop. So we'll start over at that point around noonish, right? Thank you so much. And do you have any questions?
So any more questions? No more? No more sweets?
Okay, so I was supposed to discuss something with somebody, but I don't remember what and with whom. So whoever I make the promise, please come to me and then we'll talk. Other than that, yes.
I made only one that like it's about the changing that it's that.
Yep.
Will with something that was.
Yes. We can even make an experiment. So, okay, I'll jump ahead, all right? No, I won't jump ahead. But we'll have some fun experiment. We can try to do it over here. I haven't tried it yesterday, but we can try it over during the coffee, not during the lecture. About people walking with their computers around the building. So if you walk around the building and register the SSIDs of the Wi-Fi networks that your computer receives, if the building is large enough, you will be able to detect the fact that you moved around something. And that's the experiment in which you have in this folder that I provided at the very beginning. So I actually made this walk around my house in Warsaw, but also around the institute I'm working on. And during the walk in the urban area, I was able to register order of a few hundred networks. So I'll explain the details of this experiment soonish. But this is where actually, a cosine similarity turned out to be more useful than Euclidean one in detecting the circular or maybe figure 8 motion of that I actually made during my walk. So we will see this in practice. Okay? Any more questions? All right, I'll see you soon.